Okay. Well, what I'll talk about right now is that uh, without ontology, the large language models are clueless. And I think Gary has abundantly explained that. And right now, my title is a fellow at Permion.ai. That's an AI company. It's a follow-on to a company we had some years ago called VivoMind. And we have actually been making money from these things. And that means that we have to have precise uh, control over what happens. But we also need to be able to support natural language in a very convenient sort of way, and a way that is for which the LLMs are actually very good. So we are definitely using LLMs, but we are not using them for reasoning. Now, here's an anticipation of the LLM methods. This is a classroom in the year 2000 as it was imagined in 1900 in France. And there it shows that there's the teacher who was dumping some books into this machine, and a man is, one of the students is turning a crank, and that extracts all of the intelligence, sends it over to the wire to the students. And in a sense, this is basically the goal of a lot of the technology being developed today. That it's that book that's cartoon from 1900 was a joke, but that's essentially what people are trying to do with the large language models. Now they're excellent for machine translation, but they're unreliable when they do kind of reasoning because they do not have any checks on that reasoning. And that's one of the topics that I will be discussing. Now, I have a summary here of a number of issues, and Gary has gone over many, many issues that are similar to this. And what I'll talk about is the point that human languages are derived from the way people talk about everything they see, hear, feel, and do. That means everything. And I definitely do not claim that natural languages are the language of thought, by no means. And in fact, I'll show this next cartoon, which shows why there is much more to thinking than just language. We have a policeman who is explaining answering a question that the man on the right has asked, and he's just in the mind of the policeman, he has a very clear spatial diagram, very clear and precise, and he's trying to communicate that in words. And the man on the right is the only thing he's got clear is that he goes straight ahead to a stoplight, and once you get beyond that stoplight, it's all a hopeless jumble. And that is essentially what happens in all human intelligence, that linear thinking in language is very important for communication, and it's also very important to guide much of our thinking. However, there's a huge amount more that that cannot be described in LLMs. And here are some examples from a book by Claude Vandeloise, who drew diagrams to explain spatial terms in French. And the point is that for most words, the dictionaries list many meanings, but the number of possible meanings is open-ended, and even the claim that there is some kind of a core literal meaning is doubtful. And the examples by Vandeloise show that. So here it shows he's using the word curé or priest as the person who has a rounded hat, and the minister has a square hat. So from the speaker's point of view, the speaker on the left, from his point of view, the oak tree is in front of the poplar tree because that rounded oak tree is in front of him. They're two static objects. But the moving objects, he would say that the priest is ahead of the minister, even though the priest is farther away, but because they're both moving on bicycles, the one who's moving is in front. So these are issues about even the same words being used in the same speaker in similar positions, but there are differences. Here's another example where he has four presidents who are looking at or walking towards a tree. And for all of them, for each of them, the president sees himself as being in front of the tree. But then on the right-hand side, the four presidents are walking toward a cannon, and it's not possible to say in front of now because a cannon itself has its own front and back. And so you have to use the front of the cannon, not just the front, as opposed to the tree, which is symmetrical. So any side could be the front. These are issues that people know, but the point is, our computers don't unless you give them that in some kind of ontology. Now, here's another example. The pear is in the bowl. Well, actually, the apples are in the bowl, but the pear is on top of the apples, which is actually outside the bowl. However, because the pear is being supported by the bowl and its contents, it's proper to say the pear is in the bowl, even though they're not. The pear is very definitely not in the bowl. And if you had a system of the kind that Gary was just showing, where you would take sentences and translate them to a geometrical or spatial kind of diagram, these kinds of features are critical for understanding the language. Here's another case where on the left, you say the bird is outside the cage. But on the right, it's not really proper to say the knife is outside the cage, because for a bird, it's sometimes the bird is in the cage, and it's a normal way for that to happen. But it's very rare that you would ever have a knife that is in a cage. Now, if it were for some reason in a cage, then it would be appropriate to say that it's outside the cage, but you would have to have all that background knowledge in order to interpret that sentence correctly. Here's another example of an egg yolk diagram. And this is by Lehman and Cohn. They had using an egg yolk to illustrate examples that are accurately represented, are typically representative of the word, and those that are not really that representative. So in this case, we have the word chair, and the things in the yolk, you would definitely call them chairs. They are typical chairs, somewhat different from one another, but all of them definitely are called chairs. But the ones on the egg white are strange for one reason or another. They may have wheels and a wheelchair. They may have a folding chair. It may have a rocker. And then you have things on the borderline like a toilet. When the seat is down, you can use the toilet as a chair, but it also has other functions that are more typical. And then you have things on the outside like a footstool or a chair or stairs. They could also be used. They could also be used to sit on, similar to a chair, but they're just outside the boundary. And this is typical for everything. All the words in any language are like this. And even the professional lexicographers say that they don't believe in word senses. They know that the set of word senses given in any dictionary is basically an editorial decision based on the cost and what the dictionary is designed for. So these are critical issues that you have to consider. Here's another chair. This is by Jake Kress, who carved these kinds of chairs. And if you see it in a museum, it's funny. This has happened to be in the Smithsonian. And but if you saw it at night in an old castle, it would be rather creepy. And so the meaning is always context dependent. Here's another example. People say that, oh, well, mathematics is very, very precise, right? Well, not really so much. In any textbook on mathematics, you will always find that the author has the axioms assumed for this book either stated right up front or in the appendix, because you can never be sure exactly what words any mathematician happens to be using. Now, typically, in the egg yolk, we have integers. Those are really where the word number came from. But then outside, you have negative numbers, -1. You have 0. Most original systems didn't have a 0. Then you have algebraic numbers like the square root of 2, uh, as opposed to the square root of -1, which is a complex number. And then you have the transcendental numbers like pi. And then on the borderline, you have things like infinitesimals. Even in science and mathematics, you always need to have axioms right up front in order to tell the reader exactly what you're thinking about in that very precise science. And the linguist Alan Cruz coined the term microsense for these kinds of things, like the many kinds of chairs, numbers, egg whites. And also you had to consider, for spatial terms, you have to consider the situation and the point of view. You have, in cooking, you have many methods of baking. The words frying, baking, and slicing will differ with the ingredients, the ethnic cuisine, the cook's training, the available utensils. In fact, there are no fixed set of meanings that can adequately describe a continuous or dynamically changing world. It's just not possible. And here's a cartoon. Cartoons are easy to understand even for children, but here we have on the left, this is a shoe cartoon, and at the bottom line, you can show where you can find it. And on the left-hand side, there is the owl, who is one of their standard characters, and he says, "What's it going to take to get this thing moving again?" Now, that is trivial to understand that question and in the sense that you can translate it to another language or to some sort of some sort of internal representation. But the point is, just to understand the word take, how does the word take relate to that picture? And then thing, what does that mean? There are all sorts of things in that picture. What does it mean? And what does it mean to get the thing moving again? And then you go to the next panel, and it shows that the man or the duck who's fixing the car repairman, says parking on a hill and releasing a brake. Now that's another sentence that's easy to analyze and parse, but the point is, how do you recognize what it means and what you have to know is elementary physics to know that if you parked it on the hill and release the brake, it'll run down. And then the question is, why is he saying that? Because that's not what the customer had asked for. And so there's this irony and humor. How on earth are you going to answer all that? How can you just get all that information out of this thing? Even children can understand it, but trying to understand humor is a major problem in computer science, and LLMs don't answer that either. Now, here's a problem of visualization, and that mental models that people have in their heads are more fundamental than language or logic. And the meanings that are expressed in language are originally based on perception and feelings, and thinking and reasoning are based on mental models that use the same mechanisms as perception and action. And the idea that our mental models are based on language is definitely false. Yes, you can have mental models in which named things happen to be part of the model. On the other hand, when you just walk out into nature, most of the things you cannot name, or if you do name, nobody could reproduce from your explanation. So the question is, how could computers support human-like methods? And as Gary has just shown, it's very difficult for them to do it, and large language models are not adequate. Now, here's something that even a bird brain can do that no computer can do. That robots can perform many tasks with very precise mechanisms, but they cannot handle unexpected shapes. They can't wash dishes the way people do, with an open-ended variety of shapes and sizes. They can't build a nest in an irregular tree with irregular twigs, straw, and moss. Now, birds can do this, and they can even make adjustments if you don't have their normal kind of twigs, straws, and moss. They will find stuff that you don't want them to do, and like wires and all kinds of funny things that they pick out of your garden. And so the problem is that a computer systems and computer systems guided by the LLM technology, they still do not have the flexibility of a bird, a beaver, or a human. So even a bird or a beaver are far more intelligent as far as understanding the situation than any system based on LLMs. Now, another question is sign language. And the order of signs in the American Sign Language is similar to English word order, but the syntactic features are absent and others are different. Notice that the signs are involve 3 dimensions. They involve motion, and they can involve pointing, and they're much more sophisticated than people imagine. That people who learn from congenitally deaf people who learn a sign language can be every bit as intelligent as anybody who learned from hearing. So the point is that the same neural net mechanisms that generate and interpret spoken and signed languages. So you don't have to get the signs, the language from through the ears. They can come from the visual part. And this Laura Petito did some very interesting studies. Now, I don't have time to read all this, but the point is that she studied all 4 pairs of languages. She's in Quebec and did the study in Quebec, and she studied all parents, mother and father, using all 4 pairs of languages: English, French, American Sign Language, ASL, and Langue des Signes Québécoise, LSQ. And the point is that monolingual and bilingual babies go through the same stages at the same ages for both the spoken and the signed languages. The hearing babies born to profoundly deaf parents do not babble with language, they babble with their hands, because that's the only language they have ever learned. And even though they're hearing, they don't babble, but if babies are bilingual in a spoken and a sign language, they babble in both modalities. They babble vocally and they babble with their hands. And at every stage, they express themselves with equal fluency in their spoken and signed languages. So this means something that language alone, the kind of language that people speak, are not fundamental in it by any sense, because you can get people with equal intelligence and sometimes better intelligence. And the point is that sign languages take advantage of 3D space. For anything visible, pointing serves the role of pronouns. And references to people and things that left the scene are also possible by pointing to the place where they had been. The signer can also introduce new characters and things, place them in fixed locations in the air, and then refer to them by pointing. And hearing speakers who also learn a sign language have a double advantage. They score higher on IQ tests on questions that relating and transforming images. So in fact, a person who learns bilingual, even native speaker of a spoken language, who later learns a sign language, actually increases their ability in certain kinds of reasoning, especially spatial reasoning. That's a very significant point there. Here's Archimedes. Archimedes, his eureka moment was when he stepped into the bathtub and the water rose, and that gave him the insight that a submerged body displaces an equal volume of water. And that's a mathematical principle, which is a property of Euclidean space. And scientists use that. They don't prove it. They use it to define an incompressible fluid. And about visualization, here are 2 comments. Paul Helmos is a former as a mathematician. In fact, he had been the director of the American Mathematical Society. And he said the point is that mathematics is never deductive in its creation. The mathematician makes vague guesses, visualizes generalizations, and jumps to unwarranted conclusions. And the point is that the initial stage of mathematics does not depend on deduction. It doesn't depend on the notation. It depends on visualization and guessing. And then after the mathematician has already worked out the proof, that's when the mathematician begins using the symbols and working it out. So the symbols are used afterwards. And the point that Halmos is that writing down the proof is a relatively trivial. So writing the proof is trivial. The hard part is the visualization. And Albert Einstein, a mathematical physicist, said the same thing. The words of the language, as they are written or spoken, do not seem to play any role in my mechanism of thought. He does not think in mathematics. The psychical entities are certain signs and more or less images that can be voluntarily reproduced. So the images are more important for Einstein than the symbols, although he did, of course, learn how to use the symbols, but that's not the starting point. So that's another important point. Talking about um, talking about a symbolic, a neuro-symbolic combination really doesn't necessarily mean that we want to use conventional symbols. That there are ways of thinking, even in mathematics, that don't really depend on those symbols. And Archimedes had two creative insights. And to compute the value of pi, what he did was to imagine the note that any polygon inside the circle has a perimeter which is less than that of a circle, and any polygon that is circumcising that is outside the circle and circumscribing it uh, has a perimeter that is larger than the circle. And if you increase the number of sides, you can compute pi to any desired precision. And what Archimedes did, he used 90 sixagons to derive the value 22 divided by 7, which happens to be a more precise value than 3.14. And the point is, Archimedes discovered that way back when. Here's another example. If you ask somebody, which country is closer to Africa, Canada or the USA? Well, most people would say, oh, well, they think that the United States is south of Canada and Africa is to the south, so you would think that the United States is closer. But actually, the point is that Canada has one part, namely Newfoundland, which is very far to the east, and it's much closer to Africa than Florida. And Florida, by the way, note that the two lines drawn on that diagram have exactly the same length. And notice that a line drawn from Florida to the closest point on Africa is just touching, but the same length of a line going from Newfoundland goes much farther into Africa. So the point is that the information implicit in a diagram can be very great. The point is that the number of observations, if you just have just lines, just drawing lines between things, the number of possible observations will grow as d to the n, which is the number of points in the whatever icon you're using, and n is the number used in the observation. And the point is that the information implicit in a diagram that can be far, far greater than the explicit symbols information in symbols. This is a point that the neuroscientist Antonio Damasio said, that the distinctive features of brains such as the one we own is the uncanny ability to create maps. But when brains make maps, they are also creating images, the main currency of our minds. Ultimately, consciousness allows us to experience maps as images, to manipulate those images and apply reasoning to them. So the point is that here we have a neuroscientist who is making the point that that the main currency of our mind is to make diagrams or mappings or imagery. That imagery is fundamental, and the words and phrases are generated from the imagery. The words and phrases are not the foundation for language. They are not. The words and phrases are not the foundation for language. It's the imagery that's the foundation for language, and and not the words. Here's another example. This is a Tarski-style model in the middle, which is a set of items connected by relations, and Tarski used that to as a foundation for defining the semantics of a theory expressed in symbolic logic. So the theory has a precise mapping to that model, which consists of dots and lines, and from that you can compute the denotation, which has unique values, true or false. However, that model as a diagram has only an approximation to the world. You cannot have a finite set of things that approximate a continuous world, but you can estimate whether it's a good, fair, or poor. And the point is that Tarski-style models relate the theory to a world, to a model of the world, which happens to be diagrammatic, but the engineers will say all models are wrong, but some are useful. That the engineers recognize that what they're designing is discrete parts put together, and that the models of those things can be useful. So now the different people, for different reasons, may specify different ontologies for the same parts of the world, but the results derived by the LLMs must be tested against whatever ontology is intended for whatever purpose. So the point is that all learning, from simple habits to scientific research, is based on patterns of perception and purposeful actions. And by the way, the term I prefer is the title here of neurocognitive, because symbolic implies that your neural methods are being related directly to just symbols. But the point is, you have to use every branch of cognitive science. That includes philosophy, linguistics, psychology, that anthropology, and neuroscience, and artificial intelligence. So the point is that neurocognitive is a term that I prefer to neurosymbolic, because it really means that you have to consider every single branch of cognitive science, not just some kind of artificial neural networks. And by the way, I emphasize artificial, because the point is that each one of them is just based on one kind of neurons. But in the human brain, the neuroscientists have discovered that there are over 5,000 different kinds of neurons, and they're still discovering more kinds of neurons every day. Different parts of the brain have different parts, and in fact, the cerebellum, which most artificial AI people ignore, the cerebellum has many more neurons, about 4 times as many neurons as the cerebral cortex. It's much smaller, but it does very high performance communication, very high performance computation. Well, let's see. Got a little bit more to cover, but not much. The point I want to make is that my favorite philosopher, Charles Sanders Peirce, distinguished 3 formal kinds of reasoning. And he said the first is abduction, which consists of examining a mass of facts and allowing the facts to suggest a theory. So abduction is basically guessing. You guess at or imagine something that suggests a new theory. The second kind is deduction, or necessary reasoning. He says deduction is certain, but only for ideal objects. It could be idealized objects, namely things that you have extracted from the real world and represent by some diagram or other kind of model. And but the deduction is precise only for the idealization. It's not certain for the real world. Then the third kind of reasoning is induction, or experimental research. And that's the kind where you do some kind of testing and then and then from that, you take the information from the test and you update your models. But he also distinguished the fourth kind, and he said, besides these three types, there's a fourth, analogy, which combines the characters of the three, yet it cannot be adequately represented as composite. And by the way, analogy is the foundation for the reasoning with large language models. What you do is you find some kind of pattern and see if there is somewhere in your vast amount of multiple terabytes of petabytes of data, see if somewhere there you find an analogous pattern, and then you use that pattern to make the reasoning. Unfortunately, the analogy is only approximate, and you can't be certain that it's actually the one that was intended, and that's why any reasoning that's done by large language models or the uh, GPT-like things that are based on it is not going to be precise. And now here's an example it's an example that I put together based on Peirce's examples, and also with the kinds of on the labels, the kinds of things that people are doing with artificial intelligence. So in the middle, we have oh, I see that Ravi Sharma, you've raised your hand. You have a comment, Robbie? Okay. Well, anyway, the point is that but in Peirce's theory explains the abduction, deduction, action, and induction, and this is the reasoning cycle that is very common in computer science, using the traditional methods that have been developed in AI for over 60 years. And they are by no means obsolete. They're absolutely essential if you want to do any kind of precise reasoning. And they're absolutely essential for modeling any kind of system and the computer that does any kind of precise reasoning. So the kinds of reasoning that you do with any kind of fixed machine of some sort is the kind that will be governed by the kinds of reasoning that our computer systems have been doing for the past 60 years. And if you want to have human beings interacting with a computer or interacting with another machine like an automobile or any kind of manufacturing device, the automobile you can describe with precise logic, and that means we need some method for relating precise logic to the languages that people speak. And there's where the crux is. Now, this is the Baddeley-Hitch model for a central executive. And this is something that they proposed originally in the 1970s, and they updated it over the years until this is a version they had in around 2000. The idea is that there is something in the human brain that they call a central executive. And that central executive appears to be operating in the frontal lobes where we do our basic thinking. And the central executive uses some storage. There's a phonological loop. That is what George Miller said in his talking about the magic number 7 plus or minus 2. That's the kind of reasoning for verbal reasoning, for articulatory loop, acoustic storage. That is the phonological loop. They also proposed a visual spatial scratch pad, because when you're thinking in imagery. Just think back of the diagram of the policeman who is talking to a man who needs instructions. In his mind, he has a visual spatial scratch pad with a very precise image of the map of that particular part of the world. And what in his language, he's relating that visual spatial scratch pad to the phonological loop. So he's explaining in language, he's explaining everything he's imagining in that scratch pad. However, the person who's listening is creating his or her own visual spatial scratch pad from language, and that mapping from language to the listener's scratch pad is very incomplete and inaccurate. to a great extent. And if you put this together, put this central executive together with the loop that I had before, what we have here is a central executive of an AI system in which the central executive replaces that picture of Peirce, of Charles Peirce, and what you have here is the same basic kind of reasoning methods. These are now reasoning methods of AI. And instead of a brain, what you have, what I put there is a vat of knowledge soup. And that vat of knowledge soup would contain all the kinds of stuff that they store with large language models, LLMs, but it would also contain all kinds of imagery and gestures and everything, uh, every other kind of things that pass through people's head. And so I call that the knowledge soup. And there's what we, there is my model of what I would recommend for the future of artificial intelligence. Namely, make sure that we have a system with a central executive. And when they talk about the dangers of that AI systems might somehow go awry and start taking over the world, well, you make sure you design your central executive in such a way that that central executive is a very nice, accommodating person who is behaves like an honest person who is trying to do the best for, according to the laws of the world and also ethics and all that. So here we have the central executive in the middle, and there we want a central executive that really is able to talk to people and control what is going in and out. And that central executive has free reign of using all of the tools that are available by any kind of methods of AI, including neural nets and artificial neural nets, I emphasize, not true neural nets. And all of that must be handled. And that's my recommendation for how to create systems that are dependable. And by the way, I mentioned that I am a fellow of the Fermion.ai company, and this is the kind of way that we are developing our systems. In fact, we had systems that we were developing along the similar lines 20 years ago, and the new company, which only started up a few years ago, is adopting similar kinds of methods. So in other words, but adding the LLM. So the new company very definitely uses the LLM technology. However, it has a neurocognitive system. It's a neurocognitive system in which it has a much broader range of kinds of methods of reasoning, and which include large language models, but they also include all of the methods that are listed there in red and all the methods that might be designed in the future. So the point is, that's where we're going with it. And I want to also mention that this kind of a loop has also been done many times before. John Boyd drew a four-step diagram that you can map directly to the diagram that I have on the previous page. And he drew a four-step diagram for training fighter pilots to observe and respond rapidly. And his four stages, his first two stages, observe and orient, involve the occipital, parietal, and temporal lobes of the human brain. And the next two steps, decide and act, involve the frontal lobes for reasoning and motor control, so that the observe and together the four systems of the observe does the visual input, goes to the primary visual cortex, the occipital lobes, but object recognition and naming involve the temporal lobes. The orientation, the parietal lobes relate vision, touch, and sound in cognitive maps. And I emphasize cognitive because that involves all the six methods of all the six branches of cognitive reasoning. And then the decision reasoning is under the control of the frontal lobes. And then the action schemata are patterns in the premotor cortex of the frontal lobes. Now, the point is, in emergencies, each step can be traversed in milliseconds, but the but you can also extend those OODA loops. In fact, that's what John Boyd did. He After he left the Air Force, what he did is earn a master's degree under the GI Bill of Rights, and a master's degree in economics, and he extended it for handling an open-ended variety of kinds of reasoning in he served as a consultant to all kinds of businesses. And then the final slide is an observation by Immanuel Kant. Socrates said he was the midwife to his listeners. He made them reflect better concerning that which they already knew. And he said that Platonic or Socratic questions drag out of the other person's cognitions what lay within them. And I think that's essentially what we need. We need tools that can play the role of Socrates, that can drag out the ideas from another person or also from the large language models, and they can then get digging into the what it means. Now, I want to say that the LLMs may help support a language interface, but they won't replace Socrates. However, I believe that we can design systems that can eventually evolve into something that asks questions that could even be similar to Socrates. But I don't think that's going to happen for a long, long time. So that's basically